In this video, we're going to look at mechanisms and rate where a mechanism requires more than one step to be involved in the rate. So let's take a look at this reaction. Two NOs plus two H2s can make one N2 and two waters. Now we could propose a single step where we just consider the reaction to occur as the balanced reaction shows. Somehow I'd have to have two NOs and two H2s near each other at the same time, and they would transfer the oxygens while the nitrogens would stick to each other, and you'd end up with N2 and two waters. Well, this would be a tetramolecular reaction. Generally, we think of mechanisms as mono or bimolecular, so already this is extremely unlikely. But if we did it, well, my elementary step says that there'd be K times the concentration of NO, but there's two of them, so squared, and H2, but there's two of them, so squared. That would equal my rate. This would be a fourth order reaction, second order in respect to NO, and second in respect to H2. Well, if we actually go and experiment, the real rate is equal to a constant NO squared and H2 to the first. So the proposed single step mechanism, the rate law we would see for that single step mechanism was fourth order, but the real rate law is only third order. Second in respect to NO and first in respect to H2. So our single step of combining all the starting materials at once can't be our actual mechanism. So what could be our mechanism? Well, we can think of a variety of things. Let's just take it down slightly. We say, hey, if this is our rate, what if that's our first step and it's slow? So what if we invented a first step that said two NOs and an H2 needed to combine to something? Well, what could they make? Well, we're trying to make water, and I've got an oxygen there. So I could make one of the waters. That's going to leave me two nitrogens and one leftover oxygen, so I could also make some intermediates, NO2. Well, I've gotten rid of both NOs as starting materials, and I only got rid of one H2, so I could say, hey, what if N2O and a second H2 reacted, transferred the oxygen, made N2 and a second water? Now, does this fit what we've seen? Well, if our first step was slow, then this would fit the rate law. We'd say, oh yeah, the rate, that'd be equal to some constant times NO squared times H2 to the first. As long as that first step was slow, we wouldn't include anything from the second step. Unfortunately, this is a termolecular reaction. We have three molecules that have to come together. Despite that this does fit with what we see in the real rate law, this is not ideal. Elementary steps should generally be one or two molecules. It is exceedingly rare for them ever to be three. And so despite that this fits our observation, it is not likely to be the correct situation. Well, if that's the case, if I can't just take the rate law and slap them down and declare that, well, those things must combine because I want my first step to be slow to make everything easy. Well, what else could we do? You can invent lots of things, but here's another idea. Let's do only one or two molecule steps. So what if I had a first step that, well, let's just use NOs. If your hydrogens were to bump into each other, your H2s would just make other H2s. Like there's nothing else that they can make, there's only hydrogens. But hey, if I had two NOs react, that could do different things. I could just stick them together and make, say, N2O2. This actually can happen. We'll see it in equilibriums. If we actually have NO and a second NO, the radicals can combine and you get N2O2. This alone with just pure NO in a tank is known to occur. There's an equilibrium where these go back and forth. It's actually temperature dependent around room temperature, where depending on the temp, this will either be clear or brown, depending on which species is favored. So this is a known thing that can occur. You can go between NO and N2O2. So maybe this happens to begin with. And then we have a second step. Well, that intermediate N2O2 we created, maybe that's a little bit more reactive. What if that ran into an H2? We've already used up our NOs. I've still got some H2s I need to include as reactants. And so this could make a water. What would that leave us? Well, one oxygen left, so that could be N2O and H2O. Now we still have an N2O floating around, so we need to get rid of it. And I still have an H2 I haven't used yet, so maybe these can react as well. Transfer an oxygen, I'll get N2 and another water. So this actually forces us to make two different intermediates. But it's another idea for what could happen. And that's what mechanisms are. They're ideas of what could occur. Well, let's think about it. What would our rate for each of these be? Rate K1 times NO squared. We'd have K2, N2O2, and H2. And we'd have K3, N2O, H2. So each step would have its rate for that elementary step. So where might our slow step be? Well, if our slow step was the first step, we would expect a constant and NO squared. But we know it also has to include an H2, so it can't be the first step. So what if the second step was slow? Well, in this case, this would say that, hey, our rate was equal to K2, N2O2, and H2, except it includes everything before. How do we bring step 1 of this mechanism in? Well, that's actually where our N2O2 comes from. Two NOs make N2O2. But as we said, this is actually an equilibrium. We can see this if we just have NO on its own in a container. You'll get a mix of these gases. And regardless of that one being fairly well known, the idea with an elementary step in a mechanism is that if it's fast and it's earlier than the slow step, whatever that step is, we consider an equilibrium. What does that mean? That means that there's a rate going forward where we're going to make product. Well, that's going to be some constant forwards times NO squared. That we're doing the reaction, which we saw, hey, we already wrote that one up here. However, because it's equilibrium, well, what's it mean to be at equilibrium? To be at equilibrium is to have the same rate forwards and reverse. And so there's also a rate reverse, where effectively our N2O2 is turning back into starting material. Well, if that was our reaction, N2O2 becoming 2NO, there'd be some K reverse multiplied by N2O2 to the first. The individual directions would have their own rate law, but the whole idea is that at equilibrium, those rates must be equal. so rate forward and rate reverse must be equal, so our two equations must be equal. So to reiterate there, for any fast step that precedes a slow step, we would presume that it's really an equilibrium reaction. This means that I can derive two elementary step rate equations, one for the forward, which we'd already done, K1 times NO squared, and one for the reverse, which is the product of the first step going back to the starting material of the first step, which in that case would just be some K reverse times the concentration of that intermediate. Well, they have to be equal to each other at equilibrium. That is what equilibrium represents, which means that our K forward times the starting material squared must be equal to our K reverse times the intermediate to the first power. Well, hey, I have the concentration of my intermediate equal to other things. I can divide that Kr onto both sides. And what I end up with is that the concentration of NO2 must be equal to this. Must be equal to the ratio of the rate constant forward divided by the rate constant reverse times the square of the NO concentration. Most importantly, though, is I can go plug that in here. I can go plug that into the slow step. This is how we include the earlier steps. The idea is that the concentration of intermediate that shows up in our slow step came from an earlier equilibrium. And so I can plug that in its place. What it's going to give us is that the rate is going to be equal to K2 times the K forward divided by the K reverse of the equilibrium times NO squared times H2. Well, combine our K's, they're constants, so they would just multiply together, and our rate is going to equal the K, sometimes given K prime, K combined, which is the K of the second step times the K forward divided by the K reverse. They're all combined together as constants to form a new combined constant, which would be calculated out when doing rate law calculations, times, well, NO squared and H2. Third order, twice in respect to NO, once in respect to H2. We've again accomplished the goal of finding the rate law that was experimentally determined, but this time we did it through purely bimolecular reactions. No termolecular was required. In this case, we only accomplished it by having the slow step later than the first, which often can be the case. There's no reason your first step needs to be the slow step. It does complicate calculating this out a little bit, in that we have to introduce this idea of the earlier steps being equilibriums. Equilibrium being when our rates of the forward and reverse reaction of that first step are equal, so that we can rearrange it to say that the concentration of our intermediate is equal to the ratio of those constants times the starting materials, concentration and order. So we'll do more practice with these, but this is the idea of how we combine all the steps up to and including the slow step. We have to factor in those earlier steps as how we obtain the concentration of our intermediate species in our slow step.